Hello, my name is Suvrath Arvind, and today I'll be presenting my research paper about predicting the number of sunspots per month and per quarter using ARIMA models. So first of all, what is a sunspot? Sunspots are essentially large scars on the sun's surface that appear darker, as seen by the black dots in the picture. These are caused by strong magnetic fields, which result in lower temperatures around the region. I wanted to study this because predicting sunspots would allow us to predict solar storms, a phenomena that disrupts radio signals back here on Earth. I found this topic interesting because it has a wide variety of applications, and predicting this phenomenon would be essential for the world, as it is today, to function properly. I also found out that the number of sunspots recorded follow a cycle of solar activity that lasts for about 11 years. Because of this, we realized that the data must be periodic. That is, the data should have a repeating pattern. Using this information, we believe that it would be possible to make models to predict future values. However, there is a problem. Predicting sunspots to begin with is a very difficult task, given the nature of astronomical phenomena. The data, as seen on the right, appears to be a trigonometric function, but it really is not. The peaks and troughs oscillate at different frequencies, making the data very hard to predict. Other attempts have been made to predict sunspot values, as seen by the graph created by NOAA's Space Weather Prediction Center. As the graph shows, the model was quite accurate in predicting known values, but when it came to values farther in the future, it simply did not work. This was likely caused by the model using only values of previous data points, including the predicted ones, to predict future values, and once the model made a mistake large enough, like around late 2021 in the graph, the rest of the model gets thrown off completely. This led us to the hypothesis that the only way to solve this problem would be to use an ARIMA model, which is short for Autoregressive Integrated Moving Average, or any other model that uses similar techniques to predict future points with very little error. In order to get the models working, the dataset needed to be transformed as it is too large, with its states being quite inconsistent, especially in data points further back in time. We decided that rounding would be the best way to take care of this problem, as it provides consistency, so we decided to round to the nearest month, or for simplicity, nearest tenth of a year, and to the nearest quarter of the year. This was the only way that we could have made the model understand what the data points were. We came up with two approaches to solve this problem. The first being to make a sophisticated model, and the second being to make a curve from scratch to fit the data. We would see if the models worked using the mean squared error, or the MSE, the AIC, and the log likelihood. A lower AIC would indicate a better fit, and a higher log likelihood would indicate a better fit as well. The first model we created was the AR, or autoregression model, which would check for trends in the data. Trends are long-term patterns seen in the data, and this would allow us to see if the sunspot data had long-term patterns, meaning that over time, are the number of sunspots increasing or are they decreasing? That's the point of this model. The log likelihood produced by this was quite high, but the AIC was quite high in magnitude as well. Lower AICs are good. Higher log likelihoods are good as well, but lower AICs are good. And this produced an AIC of about 310,000, which is not good at all. That means we rejected this model. The second model we created was the MA, or moving average model, which checked for seasonality in the data. Seasonality is short-term patterns, meaning that do the sunspots increase for a short period of time and then decrease, or do they decrease first and then do they increase, and is it repeating? That's the point of this model. The log likelihood produced for this model was quite high again. It was 335,000, but the AIC was nearly 700,000, which is not good at all. That means we have to reject this one as well. Then we used more sophisticated models, which were the ARIMA and SARIMA models. The ARIMA uses both AR and MA, as seen in the name, and the SARIMA uses the ARIMA, but adds a seasonal component to it as well. This means that this model is more sophisticated and powerful and takes in more parameters as a result. The results of both models are comparable with log likelihoods being roughly or being between 3 and 4,000, and the AICs being just about 7,000, which is much better than the previous two models, which had AICs almost 1 million or close to 1 million, which is not good for those. That means we should keep these two models. We also created models from scratch, the first one being one sine wave with 4 parameters that were changed. The amplitude, the period, the phase shift, and the vertical shift were all changed and can be seen by the equation on the screen. The second model we created was 2 sine waves being multiplied together. Once again, parameters were changed, except this time there were more parameters as there are 2 sine waves being multiplied together. And that the parameters can be seen in the equation on the screen once again. And to find the best one, we altered each term using for loops, and the best parameters was determined by the MSE. To find the best model, we had to find the lowest MSE out of the two. For the ARIMA model, as the graph shows, we had a very close fit with an MSE of only 460. This meant that this model was quite precise, and it can be seen that the orange curve, which was a prediction, nearly matched the original curve for most points. There's very little difference between the original values and the predicted ones. The S-ARIMA was also quite close, except its MSE was higher than the ARIMA. This meant that this was precise, but the ARIMA did better. The first sine wave produced an array of values as we changed each term. And the best model it can be seen in the right graph, where the orange curve is the prediction and the purple is the original. You can see that there's very obvious gaps between the prediction and the original, but this was the best as it had the MSE of only 20 million. 20 million is quite high as compared to the other models that we used. The second sine wave, for the second sine wave, we also created an array of possible sine waves, and the best one can be seen in the graph on the right. Here, it was even worse than the first sine wave, as the MSE was 22 million, which is bad and must mean that this was a terrible model. So of the two sine functions, the first model, which only had one function, performed better, and of the two sophisticated models, the ARIMA model performed the best. And of the 4 models, the ARIMA model was the best as it had the lowest MSE because the sine waves did not produce any other comparison factors. So that means the best model for predicting the data is the ARIMA model, even though it was not the most powerful. The S-ARIMA was the most powerful, but did not give us the most favorable results. So in conclusion, sunspot data can be predicted using models like these. The ARIMA model is the best based on MSE when compared to the sine functions, and its AIC and log likelihood were much better than the S-ARIMA or the AR or MA models. That meant that our hypothesis was correct. In the future, we could use these models to predict other astronomical phenomena. Those could include predicting when the Earth will be hit by meteorites or solar storms, as I mentioned earlier, which is related to sunspot data. Thank you so much for listening, and I hope you enjoyed this presentation, and I hope you learned something new about ARIMA models and about sunspots.